Well, welcome to the last block of this class, which will be a little bit different from the other three. First of all, it's something that is built on top of the previous three blocks. We are going to discuss some extra methods, some more advanced methods. There will be only 2 lectures in this block, and there will be no single topic for these 2 lectures. In fact, there will be about 2 different things. The first lecture, which we are going to learn in this learning sequence, is about how to analyze qualitative data and discrete data. So far, we've been working only with quantitative values. Now it's time to talk about qualitative values. Okay, and then the next learning sequence and the last learning sequence in this block will be devoted to analysis of bad data, so to speak. If you have data that is not distributed normally, for example, it doesn't follow any known distribution, it has some outliers, so distribution is skewed, what to do in this case? So in this case, you have to use non-parametric methods, and then it's a topic for the next learning sequence. Now let's talk about the qualitative data. And first of all, I'm going to remind you what qualitative data is. Okay. So remember that every time we are talking about data it's a set of observations or set of objects, and then every observation meaning that you measure or observe a certain variable, right? A variable is the characteristic of the individuals, of your objects or phenomena, and usually we have several variables. It's very rarely when in the experiment you measure only one variable. Variables can be different, right? So we already know that they can be dependent, independent. When we talked about regression, we discussed that they can be discrete and continuous, random and determined, qualitative and quantitative. Let's recall what qualitative variables are. Okay. Well, the difference between qualitative and quantitative variables is rather simple. Quantitative variables, they describe an amount. So it's something that you can measure, you can compare. So it's some numbers. Qualitative variables describe a quality, a category. And most of the time you cannot express this category using numbers. Okay. And usually most of the qualitative variables, they do not imply numerical ordering. For example, sex or gender, male and female. Okay, of course we can express male and female in numbers like 0 and 1, -1 and +1, like we did in people data. But of course it makes no sense at all. It's just a dummy variable. It's some code. Okay, and we cannot, of course, order males and females. Who should be first, right? Then, for example, color of eyes. It's the same idea. So you cannot order it. And you still can use numbers like 0, 1, 2 for different color of eyes, but it will make no sense. It's just a code. Okay. And when you recall the people data, we had at least 2 purely qualitative variables. It was region, where we coded it with -1 and +1, and then it was also the sex or gender, also coded like this. Then we also had one variable that we can treat as qualitative variable. It's a hair length. In this case, of course, ordering means order has a meaning, because -1 is smaller than +1, and the short hairs are indeed smaller than the long hairs. The length is smaller. So in this case, we can talk about qualitative variables that can be ordered. So all qualitative variables can be divided into 2 parts. Those that cannot be ordered, they are called non-ordinal categorical variables or qualitative variables. And then those that can be ordered, and they are called ordinal categorical variables. Usually non-ordinal variables represent pure categorical parameters, like, for example, color of eyes or sex. And ordinal usually are made from the quantitative variables by grouping the values, by discretizing them. For example, you can think about age groups. Instead of age in years or in days, in months, you can say, for example, below 18, between 18 and 40, between 40 and 50, and then above 50. So in this case, we can treat this variable as a categorical variable. What makes qualitative data different from the quantitative data? Well, first of all, because in most of the cases we cannot measure it, we cannot represent the qualitative variable in values, most of the statistics have no sense. So like average, mean, standard deviation. What is standard deviation for sex, right? So it's absolutely useless. But instead we can calculate 2 other statistics, which are proportions and frequencies. We already used proportions in the block 2, and in this block we also will discuss the proportions and recall how to make some inference and make some tests for proportions. Okay. And then the qualitative variables can be represented as a frequency table which simply calculates frequencies for different combinations of the levels of the qualitative variables. If you have only one variable, then you can do the following. You can make a frequency table. You can make a bar plot that represents the frequencies. You can make a pie chart, which does the same actually. Then you can calculate several statistics, including mode and proportions. If you have two variables, then you can also do a little bit extra. You can make a contingency table that tells you something about if two variables have any association or not. So we are going to discuss all these things in this learning sequence. That's an example we are going to use. I have some questionnaire for engineers in Denmark. Then we pick it up 50 or 100 engineers and ask it two questions actually. Do they know R or not? And the answer was yes or no. So you can see it in this column. And then what kind of salary they have. And we use this categorical variable for salary. So H means high salary, L means low salary, and A means average salary. Of course, we can represent this data using numbers. For example, we can use 1 for yes and 2 for no in R. And for salary, we can also use 1, 2, 3. And then, of course, in this case, I mean, it makes no sense to use this 1, 2, 3. It's just a code. It's just a dummy variable, right? Then that's the questions we are going to answer. First of all, can we say that most of the engineers in Denmark know R? And then can we say that most of the engineers have salary higher than the average? And can we say that is there any relationship between knowledge of R and the salary level? Okay, so that's the plan for this learning sequence, one of the plans. So the simplest thing we can do is to compute a frequency table. Frequency table is a following. You just calculate how many values you have for each level of your categorical variable. For example, in the first case where I asked about R, we have 30 engineers that answer it no, and then 20 engineers that answer it yes. So in this case, we have we can calculate the relative frequency. That, of course, it will be a proportion. So in this case, we have 60% of engineers who don't know R in our case, and then we have 40% who know R. And the total amount of answers I got was 50. Okay. In the second case, I have the salary. So 12 engineers told me that they have a low salary. 24 engineers out of this 50 had average salary, and then 14 engineers have high salary. And then we can calculate the relative frequency just by dividing these values to 50 to the total number of answers. In R, you can make these frequency tables very quickly if you use this function table. If you apply table to any variable, any column of your data frame, you will get a frequency table. And then you can calculate the proportions, the relative frequencies, just by dividing the frequency table values to the total number of values, like it's shown here. Then you can represent the frequencies, either real frequencies or the relative frequencies, using a bar chart. So in this case, it's a very simple thing. You have a bar plot, and height of bar corresponds to either frequency or relative frequency. And I must say that that's the best way to represent the frequencies, because it clearly gives an idea how big the frequency is, and it clearly it allows you to compare the frequencies quite clear. Okay. The second, probably more popular way to represent frequencies, using pie charts. And I never recommend pie charts, just for one reason. If you have a pie chart for example, only for two categories, so you have only two pieces of this pie, that's okay, because in this case you can clearly see what is what, right? Also, if you have several pieces but with a very clear difference, for example, you have 10%, 30%, and 50%, 60%, then you can also use pie chart. But in most of the cases, pie chart is useless because it doesn't give you a clear idea how big the difference is. For example, in our case, we know that the low, we have 24% here, 24% here, and 28% here. But if you look at the pie chart, you don't see this difference clearly, right? These two pieces, they look similar. Okay, so they look almost the same. So use bar charts or bar plots instead of pie charts. That's my recommendation in this case. So that's how to represent the qualitative data. Now let's talk about how to calculate statistics and make an inference.